Thanks for stopping by the eCave today. In this second episode, I'll be talking about 3.5-inch diskette drives and the interface to them. So in this one, I'm specifically going to be focusing on the interface between the Model 30 PS2 machines and the IBM Diskette drives supplied with them. So if you're interested in that, why not join me in the eCave? Well, thanks for staying. Yes, this is part 2 about the 3.5-inch diskette drives. In the first episode, I spoke about the industry standard interface between the floppy controller and the diskette drives. Plus, I also talked about the pull-up resistor currents and show you some of that. Now, if you haven't seen that episode, I would encourage you to do so because I'll be building on what I spoke about there, so I won't be covering the same things. Now, this episode focuses on the differences which IBM applied to the IBM PS2 Model 30 286. This machine was, of course, one of the pioneers in using 3.5-inch diskette drive. So IBM chose to take a different approach in those early days. However, before jumping into that, I have to confess that I discovered that the motherboard I've been using to do all my research into the diskette interface is faulty when it came to the diskette drive. The motherboard is able to read a diskette fine, and I can boot up from the startup diskette. But when I try to format or write anything to the diskette, it doesn't work. It gives me the retry abort error. Now, initially I thought it was the diskette drive itself, so I took another IBM diskette drive and swapped it out with the same results. So there's something wrong with that interface. Now, after diagnosing the interface, I did find the problem. It boils down to the fact that the sense line 8 from the diskette drive isn't being passed to the NEC 765 floppy controller. The sense line 8 is the index pulse from the diskette drive when the spindle motor is turning. Now, according to the schematic of the IBM motherboard, the index signal is passed into the IBM proprietary CMOS Asic chip, and then from there it is passed to the NEC 765 floppy controller. Now, on the oscilloscope, I could see the index pulse coming from the diskette drive on sense line 8, entering the CMOS Asic IC chip on pin 65, as you could see on the schematic diagram. However, when I was probing the CMOS Asic output on pin 39, there's no output. It's dead. Now, this told me the CMOS Asic isn't passing the index signal to the NEC 765 floppy controller. Now, these are custom CMOS Asic chips and they are simply not available, so I can't get a new one, unfortunately. Well, I didn't give up because it occurred to me that if the CMOS Asic isn't passing the index pulse to the floppy controller, maybe I could bypass it and send it directly to the floppy controller. Well, after some testing, I found that it could work, but only if I inverted the index pulse, because that appears to be what the CMOS Asic does. The index pulse arrives at the CMOS Asic as a negative going pulse, but comes out as a positive going pulse into the NEC floppy controller. Now, the solution I came up with was simply to isolate the NEC 765 pin 17, which receives the index pulse, and put a hex inverter in series from the line 8 on the diskette drive and into the floppy controller. Now, initially I disconnected the signal line from the CMOS ASIC and took it directly into the NEC floppy controller. I did find out doing that the motherboard couldn't even read or write diskettes if I bypassed the CMOS ASIC. So I then reconnected the CMOS ASIC, and I'm simply tapping the index pulse from the diskette drive on the CMOS ASIC and sending it through the hex inverter and then into the NEC pin 17 on the floppy controller. And thankfully, that worked fine. Now, that of course tells me that it's not the input on the CMOS ASIC that's bad, it's actually the output between the CMOS ASIC and the NEC floppy controller. So go figure how that has gone bad. I have no idea. Now, let me show you how I prototyped this fix and then moved on to make it a bit more permanent. So here's my setup. Basically, I've got Checkit doing a test on the diskette drive while using a couple of oscilloscope probes. And as you see here, I've lifted up pin 17 on the floppy controller chip. I'm putting that into a small breadboard, and I'm tapping off the index signal, which is this green wire on wire number 8, and putting it into the 8C04 inverter, one of the inverters. And it goes into pin 1 and comes out at pin 2 into the floppy controller. And this appears to be working fine. So this fix has done the trick. As you see, I glued the hex inverter chip, which is a 74LS04 IC, on top of the floppy controller, and then used some wires to get plus 5 volts and ground from the pins on the floppy controller, and then tapped off the CMOS ASIC output into the floppy controller input on pin 17, which I isolated from the motherboard, so it wouldn't be, signal wouldn't be drawn down because of the bad interface between the floppy controller and the CMOS ASIC. So that worked fine. I'm very happy with that, and it hasn't missed a beat since I did that fix. So with all of that working, I continue to do my research into the IBM interface, and it's time to share that with you. And I'll be using the same overview I did in the first episode, but I'll be skipping most of it and primarily focusing on what IBM did on the interface to which is different from the industry standard one. So let's get to that. Now, this is what I showed you in the last episode, so I won't repeat that here. Let me flick to the control lines. So here are the main control lines I showed you in the last episode, but hey, there's a new one here, number 2. IBM have added something called high density control line. So what does this one do? Well, let's go into that. Well, as you see here on the schematic diagram for the IBM 3206 motherboard, the control line 2 comes from the IBM proprietary ASIC chip. It is not coming from the NEC 765A floppy controller chip. The IBM designers decided that they would need a method to tell the diskette drive when to format a 1.44 megabyte diskette as opposed to formatting a 720K diskette. So when you use the DOS formatting command without any parameters in IBM PC DOS version 3.3, the Model 3206 would format a diskette as a 1.44 megabytes. The BIOS would activate the control line 2, which pulls it low, and the diskette drive would know to format the diskette as 1.44 megabytes. On the other hand, if you wanted to format a 720K diskette, you had to add the sector and tracks parameters to the format command, and the BIOS would pull the control line too high and thereby tell the diskette drive to format the diskette as a 720K diskette. Now, of course, the only diskette drives to act on these control lines, I'm assuming, are IBM Diskette drives in the Model 30 machines. Now, after some testing, I also worked out that the IBM Diskette drive will simply refuse to read either a 720K or a 1.44 megabyte diskette, depending on the status of the density control line. This is because of the next signal line added by IBM as well. So let's have a look at that. Here we have the sense lines, which are the lines coming from the diskette drive to the floppy controller. This is where the IBM designers chose to add a new sense line using signal line 4. This sense line wasn't documented in IBM's technical reference manual for the Model 30 machines. In those manuals, it's simply marked as reserved. However, in some later manuals, IBM refers to this sense line as drive type ID 1 when talking about the 34-pin IDC diskette interface. You can see IBM's description for the sense line from the diskette drive here below. It says, these signals provide encoded drive type information to the system when the drive is selected. For the Model 30 machines, this is exactly what happens based on my investigations and testing. The key word here is when the drive is selected. So let's look at that in some more detail. The IBM Diskette drive activates this sense line every time the diskette drive is selected. As you can see on the schematic diagram, this sense line is not going to the NEC 765 floppy controller IC. Instead, it is being sent to the Intel 8742 keyboard controller. You can also see that the sense line has a 3.7 kilo ohm pull-up resistor, which by default makes the line high. Now my testing has revealed the following. Every time the diskette drive is accessed with the drive select control line, the IBM Diskette drive will either pull the drive ID sense line low or high. If there is no diskette in the diskette drive will pull the drive type ID sense line low, because the IBM Diskette drive attached is a 1.44 megabyte drive. It seems to be the default if the drive doesn't have a diskette inserted. Now, if a diskette is inserted into the diskette drive, it will pull it low if the diskette is 1.44 megabytes and pull it high if it's a 720K diskette. Now, this behavior was probably designed to tell the BIOS which type of diskette is inserted into the diskette drive, so the BIOS can update its data tables for DOS, so DOS will also know which type of diskette is inserted. I'm guessing the default behavior of pulling the drive type ID sense line low without any diskettes is done because the diskette drive is, of course, by default a 1.44 megabyte drive. Now, what happens if the drive type ID sense line is disconnected from the diskette drive during a boot process? This, of course, is the case if you attach a non-IBM Diskette drive to the interface. Well, during the boot process, the BIOS will detect the signal line as a high due to the pull-up resistor on the motherboard. This in turn tells the BIOS that the attached diskette drive is a 720K drive, which the BIOS in turn tells the operating system by updating the BIOS data area in memory. The data area holds the equipment list and the attached equipment capabilities. Now, how does the BIOS detect this? So let's look at that. As you see, the drive type ID signal line is sent to pin 33 on the Intel keyboard controller. Pin 33 is bit 6 of the keyboard I/O port 64, which consists of bits P10 to P17. You can see some of the other bits are used for parity detect for the memory sims plus data in for the mouse and keyboard. There's even a detection for the plus 5 volt fuse on the motherboard, which supplies the keyboard with power. So this can be handy to know because the Model 30 gives you an error that indicates a blown fuse for the keyboard. Anyway, it's the machine's BIOS which reads the I/O port 64. It uses bit 6 to tell if the attached diskette drive holds a 720K or a 1.44 megabyte diskette. Coming back to my earlier explanation on the control line IBM calls high density, when you have an IBM drive like this, it also relies on a drive type ID sense line. There's an interaction between the two. I'm assuming when you insert a diskette into the IBM Diskette drive, it will set the sense line either high or low as soon as you do anything to select the drive with a diskette inserted. This in turn will also toggle the control line high density to reflect the size of the diskette in the drive. Now, this explains why the diskette drive is unable to read either a 720K or a 1.4 megabyte diskette if this sense line is missing from the IBM drive because the BIOS doesn't know the density of the inserted diskette in the drive. Or at least that's what I'm assuming. In order to validate this behavior, I wrote a DOS program to read the status of the bits from I/O port 64. It was a bit tricky, as you can see in the comments about the output from the program. Now, as you see, when the machine is booted and bit 6 is 0, the BIOS configures the diskette drive as a 1.44 megabyte drive. To show you that, I've got a screenshot from the test program CheckIt, where it clearly shows the maximum capacity of the diskette drive is 1.44 megabytes. CheckIt uses a BIOS equipment data area from memory to determine the capacity of a diskette drive. If you then disconnect the sense line drive type ID from the diskette drive before a boot up process of the Model 30, the bit will be high, telling the BIOS it's a 720K diskette. This is because of the pull-up resistor on the motherboard you've seen earlier. So at boot time, when the BIOS detects a high device type ID signal, it simply assumes the diskette drive capacity is only 720K. You can see that again here when I use CheckIt to test the diskette drive. It now claims the drive is only capable of 720K. So be aware. If you then look at the configuration using the startup diskette, it will always tell you that the diskette drive is 1.44 megabyte capable. That is regardless of the diskette drive type. It means that if you leave the signal line disconnected, i.e. high, The BIOS will update its configuration table for the diskette drive as a 720K during the booting process and pass that to DOS. This explains why when people attach a non-IBM 3.5-inch 1.44MB diskette drive to the Model 30, they can only read or format 720K diskettes. The setup config will tell them it's a 1.44MB drive, however the BIOS and DOS configure it as a 720K drive. If you do have a non-IBM drive, you have to ground signal line 4 to make the BIOS and DOS know it's a 1.44MB drive. Now, once signal line 4 is grounded, everything will work fine. Another difference on the interface is the power. The IBM designers chose to supply the power to the IBM diskette drive via the IDC ribbon cable rather than to have a separate power cable as most other diskette drives have. The IDC ribbon cable line 6 carries the 12 watts and the line 3 carries the 5 watts. If you are attaching a non-IBM diskette drive, these lines must be cut on the IDC ribbon cable in order to not damage the diskette drive or the motherboard. And you have to attach that standard 4-pin plug non-IBM drives support for power. Now, in the last episode, I spoke a bit about pull-up resistors and the current load on the TTL logic. I also told you that the typical pull-up resistor values on industry standard 3.5-inch diskette drives and motherboards seems to be about 1 kilo ohm. This is certainly not the same on the IBM motherboards and the 3 IBM diskette drives I have from the Model 3286, so let me show you. As you see here, I measured the pull-up resistor values on the 2 IBM 3286 motherboards, the Type 1 and the Type 2. In addition to the pull-up resistor values on the 3 diskette drives for these PS2 machines I have. Now, as you can see, the pull-up resistors are far higher on the motherboards and the diskette drives. The motherboard pull-up resistor values are in the mega ohm range, whereas the diskette drives are mostly 10 kilo ohm, although one of them stands out with mega ohms pull-up resistor values. I can only assume that this is because of the CMOS custom ASIC IC, which interfaces directly to the diskette drives rather than the NEC 765 floppy controller or some TTL logic in between. I would at least check any diskette drive for the pull-up resistor values before attaching a non-IBM diskette drive to this interface. If the pull-up resistor values are far less than 1K, I'd be concerned about the high current value going into the motherboard of the IBM Model 30, so be aware of that issue as well. I hope this has clarified some of the mystery in relation to the IBM interface and how they chose to implement it all the way back in 1987. It was probably one of the first machines to use 3.5-inch diskette drives. Probably not the first, but one of the earliest ones. Now, one of the more interesting issues I covered was the pull-up resistor values on the diskette drives, and the fact that one of the diskette drives has a pull-up resistor value of 10K, whereas the others have pull-up resistor values which are in the 5 to 6 mega ohm range. So of course I proceeded to repeat my current measurements like I did in the first episode. This time I measured the pull-up current values on both of the different IBM diskette drives. I'll show you first the one with a 10 kilo ohm pull-up resistor value, and then the other one, which is the 5 to 6 mega ohm pull-up resistor values. Now I'm again using Dave Dunfield's IMD program, and I'm measuring the pull-up current while changing the head from head 0 to head 1, and this is control line 32. So here we have the Mitsubishi IBM drive, which has the 10 kilo ohm pull-up resistors. We're running here head 0, and I'm also, of course, measuring the current through signal line 32, as you can see here. And the yellow trace shows high IF 5 volts. So, and the current, as you can see, is higher than on the high impedance pull-ups, but it's 0.02 milliamperes. Now let's change to head 1. As soon as I press H, signal goes low. Head 1, and the current is now 0.479 milliamps. Not much current at all. This is sort of representative of most of the signals that are terminated on the diskette drive. So I'm running IMD on a diskette drive. This is the YD701 diskette drive with a high impedance pull-ups. I'm on head 0, and head 0 means the yellow scope line is high, i.e. 5 volts. And you can see the pull-up current here, which I'm measuring on signal pin 32, is practically non-existent. So if I change to head 1, so I'll press the H key. It's now on head 1. The signal has gone low, so the line's been pulled to ground, and it's even less current. Very, very small current. Well, that was interesting. The pull-up current on the IBM drives is very low indeed, in the micro or nano range. Anyway, I do wonder why the IBM engineers chose to do this and then later on change the diskette drive pull-up resistor to some mega ohm values. The interesting fact, though, is those two drives have exactly the same part number, so it's strange, so go figure. Anyway, I hope this episode has shed some light on how IBM did the diskette interface differently to the industry standard, or what later became the industry standard. Now, if you do know anything more about why IBM chose to do what they did, or some reasons for it, I would love to see some comments about that or be more informed. So don't be shy. So with that, thanks for spending the day in the eCave with me, and until next time, goodbye.